This is homework, chapter 13. In this session, we will be solving problems 1, 4, 5, 11, 12, 20, and 23. Problem 1 reads, what is the ratio of the gravitational pull of the sun on the moon to that of the earth on the moon? Assume the distance of the moon from the sun can be approximated by the distance of the earth from the sun. Use data in appendix F. Is it more accurate to say that the moon orbits the earth or that the moon orbits the sun? Okay, so we're going to take the ratio of the G, what is it, mass of the moon, mass of the sun, distance moon sun squared, divided by G, mass of the moon, mass of the earth, distance moon earth squared. All right, so these G's go, and so does the mass of the moon. So we've got a mass of the sun over distance moon sun squared, divided by mass of the earth over distance moon earth squared. All right, I guess I need to get those values. So let me pause. Okay, so we're going to have 1.99 times 10 to the 30 kgs divided by 1.5 times 10 to the 11th meters. That all divided by 5.98 mass of the earth times 10 to the 24th kgs divided by 3.84 times 10 to the 8th meters. Oh, by the way, this is squared. And this is squared. And your ratio is going to be 2.18. (13.4) reads, two uniform spheres, each with mass m and radius r, touch each other. What is the magnitude of their gravitational force of attraction? So we got this. This is r, and this is r, and that's m, and that's m. So it's just simply g times 2m divided by 2r quantity squared. So it's going to be g 2m 4r squared. Oh, wait, yeah, radius r or radius r. Okay, that was 13.4. 13.5 says two uniform spheres, each of mass 0.260 kg, are fixed at points A and B. Find the magnitude and direction of the initial acceleration of a uniform sphere with mass 0.10 kg if released from rest at point P and acted on only by forces of gravitational attraction of the spheres A and B. So it looks something like this. You got A and B. You got P here. That's right in the dead center. This is a 0.260 kg, 0.260 kg, and this is 16 centimeters, that distance. And this guy is 6 cm, and this mass is 0.010 kg. All right, this is 10 centimeters. And similarly on the other side as well. Okay, and now I think it's pretty obvious from the symmetry of this problem that the forces in the x direction, if you take this as 0, this is 8 centimeters, and that's 8 centimeters, are going to be equal to 0, and they'll cancel each other out. So all we need to worry about is the forces in the y. So force A in the y is going to be equal to F A cos, what is this? Well, whatever this is that 6 centimeters? Oh, how big is that? Yeah, FA cos theta, which is going to be 6 centimeters, which is FA times 0.6 meters, or 0.6. And then FB of y is going to be equal to the same thing, FB 0.6, and they're all going in the same direction. And they equal to 104 times 10 to the negative 11 newtons twice. So you multiply that by 2, and you're going to get 2.1 times 10 to the negative 11 newtons. Oh, now we're supposed to find the acceleration, right? Are we? Yeah. Find the initial acceleration. Okay, so that's good. F equals ma. So we take 2.1 times 10 to the negative 11 newtons divided by 0.01 kg, and we are going to come up with an acceleration of 2.1 times 10 to the negative 9th meters per second squared. All right, and that was 13.5. All right, 1311 reads, at what distance above the surface of the Earth is the acceleration due to Earth's gravity 0.980 meters per second squared if the acceleration due to gravity at the surface has a magnitude of 9.80 meters per second squared? So in order to solve that, you note that the acceleration A is reduced, is a 1/10 or 0.1. So we take the distance has to be reduced by a factor of a tenth, right? So it's going to be the square root of 10. I'm sorry, the distance has to be increased by that amount. Okay. Right, because you want to get F is equal to 1/10 of F. So 1/10F. So now we've got this guy has got to be, that's in the denominator, and you square it. So you got to take the square root of 10. So the distance has to be increased. Okay, so this is going to be our total distance. Square root of 10 times the radius of Earth will give us that new force. But then we got it asks for the height above the surface of Earth. So that means we've got to subtract the radius of Earth from that value. And you're going to come up with, let's see, 1.38 times 10 to the 7th meters. All right, 1312 reads, the mass of Venus is 81.5% that of Earth, and its radius is 94.9% that of Earth. That's why it's called our sister planet. Now it says, compute the acceleration due to gravity on the surface of Venus from this data. So we know G equals G and mass of the Earth, radius of the Earth squared. So now we're going to have G Venus, or acceleration Venus, probably incorrect to call it G, equals 81 equals G times 0.815 mass of the Earth divided by 0.949 radius of the Earth, quantity squared. And you're going to get 0.905 G. So almost the same. Okay, part B asks, if a rock weighs 75 newtons on Earth, what would it weigh at the surface of Venus? So here we go. 75 newtons. 75 newtons, but we don't have, not times 1 times 0.905 equals 67.9 newtons. All right, that was 13.12. Okay, for number 1320 reads, an Earth satellite moves in a circular orbit with an orbital speed of 6,200 meters per second. Find the time of one revolution of the satellite, the radial acceleration of the satellite in orbit. Okay, for the time of revolution, we need to find R. So G, M1, M2 over D squared, R squared, right, is going to be equal to M V squared over R. So over D, so I'll take one of these out and I'll take the mass of the satellite out. So V is going to be equal to the square root. I'll just do V squared is going to equal to G mass of the Earth over D. So V squared, D is going to equal to G mass of the Earth over V squared, which we're going to get, let's see, R is going to be 1.04 times 10 to the 7th meters. So that's our radius there. Now we're supposed to find out, okay, that's R. Our period is T equals V over, V equals the distance 2 pi R divided by period. So T equals 2 pi R over V. So this is going to give us 2 pi times 1.04 times 10 to the 7th meters, and then divided by 6,200 meters per second. It's going to give us some answer in seconds. Is going to be equal to 1.05 times 10 to the 4th seconds. And if you wanted to know hours, you would divide by 3,600 seconds. But I guess we don't need to know that. So let's see, let me pause this, get some board space. All right, A radial is going to equal to V squared over R. It's going to be equal to 6,200 meters per second. Quantity squared divided by 1.05 times 10 to the 4th seconds. And that's going to give us 3.7 meters per second squared. 3.70 meters per second squared. That's our radial acceleration. Okay, so 1323 says two satellites are in circular orbits about a planet that has a radius of r equals 9.00 times 10 to the 6 meters. One satellite has a mass m1 equals what is it? 68 kilograms. And orbital radius of 7.00 times 10 to the 7 meters. So D1 equals 7.00 times 10 to the 7th meters. Okay. The second satellite has a mass of equals 84 kgs. And an orbital radius of 3 times 10 to the 7th meters. D2 equals 3 times 10 to the 7th meters. Oh, this one has an orbital speed here. V equals 4800 meters per second. Okay, so now it wants to know what is the orbital speed of the second satellite. Okay, now we know that G, M of the planet, M of the satellite, divided by D is going to give us M of the satellite times V squared. Oh, this is D squared, sorry, over D. Okay, so let's see, the mass of the satellite can go, and one of these D's can go with that. So now we know that G, mass of the planet, equals dV squared. And now as soon as we get the mass of the planet, we can figure out the other one. So let's see. But another way to do it would be like G mass of the planet, this is D1 V1, equals D2 V2 squared. So we could set up D1 V1 equals D2 V2 V1 squared, V2 squared. So we need to know V2. So V2 is going to equal to D V2 squared. D1 V1 squared divided by D2. V2 is going to equal to the square root of D1 divided by D2 times V1. The square root of V1 squared. Okay, and that's going to give us, let's see, 7,330 meters per second. 7.32 reads, a uniform spherical 1,000 kilogram shell has a radius of 5 meters. Find the gravitational force the shell Earth exerts on a 2 kilogram point mass placed at the following distances from the center of the shell. 1 is 5.01 meters. 2 is 4.99 meters. And 3 is 2.72 meters. All right. For 1, okay, so F1, F2, F3. oops. Come on. Equals to G, mass of the, what is this, like mass of the, what's the second mass? Let's see. 100 kilogram. Okay. All right. So it's 6.67 times 10 to the negative 11 newtons meters squared over kg squared times 1,000 kg times 2 kgs, right? 2 kgs. 2 kgs divided by 5.01 meters quantity squared. And you do that with F2 and F3 replacing the 5.01 with 4.99 and 272. And you're going to come up with values of let's see. For the first one is 5.31 times 10 to the negative 9th. 5.31 10 to the negative 9th newtons. All right. Let me figure out for the rest. Okay, so now for F2 and F3, that distance, this is smaller than that. So that point mass is inside the shell. So for a point mass inside a spherical shell, the force is 0. So that's going to be 0 and that's going to be 0. And that was 13.32.